the 3rd century BC, King Hiero II, the tyrant of the city-state of Syracuse, commissioned a crown to be made by a goldsmith. And this crown was a crown of leaves like you would see on Roman emperors and stuff. And he gave the goldsmith the gold and then paid him to make the crown, and later became suspicious that the goldsmith had cheated him. Now, this crown was to go onto the statue of a god or goddess, and so he couldn't test it in any way, and he couldn't break it. It was sacred, and so he didn't want to offend the gods, and he needed a way to figure out if he had been cheated. So he approached Archimedes and asked Archimedes to figure out, is the crown pure gold, or did the goldsmith cut it with some lighter things like silver? It had the right weight, but it's this delicate wreath of stuff, and they didn't have the measurement techniques back then to be able to figure out if that crown was pure gold. They didn't have beakers and graduated cylinders and things like that, so Archimedes was stumped on this for a good while. And he came up with a solution when he was stepping into the bath one day. He got into the bath and he realized that as he got in and the water level rose, that he felt lighter. That as he displaced the water, he felt proportionally lighter based on how much water he displaced. So what he did is he devised a scale, and on this scale he hung the crown on one side, and on the other side he hung an equal amount of gold, or what should be an equal amount of gold, and made sure that they balanced. Now, they already knew it was the same weight. That's not the issue. He took that then and he submerged it into water. And when he did so, the thought process was this: if that crown is cut with a little bit of silver, which doesn't have the density of gold, then it's going to displace a little bit more water. It's going to have a little more volume. If it pushes more water out of the way, then it's going to feel a greater upward force, a greater buoyancy, and the scale is going to tip. And if it isn't, if it is pure gold, and they get it to balance and you submerge it in the water, then the scale won't tip. And as the story goes, they tried it, the scale tipped, and unfortunately for the goldsmith, Hiero didn't take that very well, and probably well. So that is the story of King Hiero II's crown and Archimedes. How true is it? Nobody really knows at this point, but Archimedes was pretty famous for some very, very clever solutions to things. In any case, Archimedes was the one who discovered the relationship between a displaced fluid and buoyancy. And specifically, what we call Archimedes Principle says that the buoyant force on an object is equal to the weight of the fluid that it has displaced. You've experienced this if you've ever played around with, say, a ball at the beach. You take the ball, and as you press it in the water, it gets harder and harder to push. As it pushes more water out of the way, it gets a greater and greater buoyant force up on it. And a ball this big is going to be really hard to push underwater. You probably don't weigh enough, and therefore it could serve as a flotation device. So another one is if you've ever picked up a really heavy rock in the water. You pick it up, it's big, it's probably bigger than you can really pick up, and then you lift it and you go to throw it, and as soon as it comes out of the water you realize, oh no, I can't hold it, and you drop it. Most of us have experienced something like that, and it's because the water's pretty heavy, and so when it's displacing a good amount of that water, the object is going to feel that much lighter. So the equation is this: buoyant force is equal to the weight of the displaced fluid. Weight is mg. M is not always obvious here, so density times volume, not of the object, it's density times volume of the fluid. Now mind you, if the object is all the way underwater, then the volume of fluid displaced is equal to the volume of the object. If it's only partially underwater, those numbers won't be equal. We use Archimedes Principle in all sorts of technology. So, for example, antifreeze indicators. So when you mix water and antifreeze to put in your car, the density of the antifreeze and the density of water are different. So we have little plastic balls that will float depending on the density. And so you might, for one thing, mix it until the orange ball floats, and for another you mix it until the blue ball floats, or whatever. That's one piece of technology that we use for that. Hot air balloons are another. Blimps. We're displacing the fluid of air in that case, but it works, right? Submarines are another. And submarines, we just stole the idea from fish, who who seem pretty shocked about it. Fish have air bladders that they will expand and contract in order to displace more or less water and then move up and down. They can just hold that position without having to actively swim. Submarines do the same thing. We pull in water if we want to sink, and you push out water if you want to float. Obviously, boats are another example of Archimedes' principle. So there you have it. Those are the principles of hydrostatics, which is the study of fluids when they're not moving. Let's move on in the next video to hydrodynamics, the study of moving fluids.